so welcome to Banker's Algorithm. And what we're going to talk about in the Banker's Algorithm, basically, what Banker's Algorithm is, and how does it work, right? And when we talk about Banker's Algorithm, there's a couple of data structures that we have to be familiar with, right? But basically, we assume that there is a multiple instances of a resource, right? And each process must have some claim and maximum use, right, of the particular resource. When a process requests a resource, it may have to wait, right? So it doesn't get the resource immediately. And when all the resources and when a process basically gets all the resources, it must return them in some kind of finite amount of time. So it actually, when you get all the resources, you get to finish your process basically, right? Now, the data structures for the banker's algorithm, basically, again, we mentioned that the number of processes and the number of resources, right? So this is n. We assume that there's an n number of processes and m number of resources, right? So basically, we keep track of available maximum, what's available, right? What's the maximum, what has been allocated, and how many more that's needed, right? So it's called a banker's algorithm because it's basically banker's algorithm idea is that it works like keeping keeps information in check, kind of like a banking system, right? So now, let's look at this algorithm more closely, right? So again, we have we have a notation J here, right? So if we have some kind of a, J indicates the which instances, right, of a particular type is available, right? So when we say max of the n times n matrix, basically we identify it as k, right? So maximum of I and j equals to k. Then what this means is that process pi may request at most k instances of resource type rj, right? So that's the idea, that notation that we have, right? So if we have an allocation of ij equals to k, then a process I here, right, is currently allocated k instances of resource j, right? So what basically this means, that this process currently holds that resource, right, as much as k, right? So, and then we have need, right? N times m matrix need ijk, same thing, but basically it says how much a process may still need uh, for a particular instance of rj, right? So remember, the process is could be many process, p1, p2, p3, p4, p5. There are many resources, R1, R2, R3, R4, right? So this is what we have to be, that's the notation that we're going to use. Now, the banker's algorithm basically consists of a safety algorithm and a resource request algorithm. And we'll go through this and see how it works basically later, right? More as the next slides, right? Now, the safety algorithm basically works on two notations here, right? So we have work equals to what's available, right, and finish which equals to whether it's finished or not, right? So so we need to find an I, right? uh, Such that it is false, right? That means it's not finished. And the need of that process is lesser or equal to the work, right? Otherwise we go to step 4 right here, right? So if it doesn't exist, then we go to step 4. That means it's finished. And if it's not, then we continue with the work and try to allocate more resources, right, until the finish is true, right? um, and basically this is the algorithm, safety algorithm. We're gonna look through this a bit more later about how it works. This is just a general overview first, right? Now the resource request algorithm for a process, basically we have a process request I, right? So if the request is lesser than need, then go to step 2, right? If request is lesser than what's available, go to step 3, and we start to allocate this, right? Now we say that it is in a safe state if the resource are allocated to PI, and if it's unsafe, that it must wait and the old resource allocation state is basically restored, right? Basically in this case. Okay, so let's look at a full example here, right? Previously this is a bit confusing, by just words, so let me just show you by an example here, right? Basically assume that we have 5 processes starting from P0 to P4, right? And there are 3 resource type, right? So we say there's resource type A, resource type B, and resource type C, right? And for the first resource A, we have 10 instances. For the second resource, we have 5 instances. And for the third resource, we have 7 instances, right? So what you want to do is first find out what is allocated, right? So if we find out what is allocated, right, usually this is this algorithm will start with a particular situation, right, or snapshot at a certain time, right? So suppose right now, right, what's being allocated, that means what process currently holds, right? So P0 holds 0 of A, 1 of B, and 0 of C, right? Remember, A has 10 instances, right? It doesn't hold anything of this. It has 1 of this and 0 of this, right? 0 of C, right here, right? So this basically a snapshot would usually be given to you to describe what it is right now, right? So your job is basically trying to see whether there's whether the current resource available and what's currently needed would cause any problem, right? Now let's look at the maximum for P0 right now, right? Um, you know so if we look back, what is maximum right here? Max is process P may request at most k instances of that particular resource. So let's look back into this example here. At time 0, right, the max here is that it may require 7 instances of A, right? May require 5 instances of B, right? So we have 5, it requires all 5, right? It requires only 7 out of 10 on here, and only a 3 from C, right, out of 7, right? So that makes what's available right here. So available will be 3 3 2, right? How do we get this number, right? Now if you look at this, it requires 7, right? Now 10 minus 7 gets you 3, right? Because there's 10 instances of A, and it only at maximum requires 7, so the remaining balance is 3, right? Now for B, the maximum that's available is basically 5. It requires at maximum 5, but remember, you know, in here, currently available says here that's currently available is only 3, right? So if you look at this, maximum is 3, and if you look here, currently available is 1 2, so 5 minus 1 minus 2 is 3, right? Same thing here as well. We have maximum it requires 7, there's 10 instances, but currently 2 3 and 2 is sold by P1 P2 P3, so now we only have 3 here, right? And right here we have it requires a maximum 3. It has none so far, but 5 has been held so far by process 2 and 3 and 4 here, so we find that available is only 2, right? So this is what's available, right? And this is the maximum that's required by each resources, right? So that's basically how the bankers algorithm work here, right? At a particular snapshot. Again, remember, so this is what the process needs, this is what the process currently holds, or all the process currently holds. So what available is basically the maximum, right? The ones that are available, right, minus the ones that are available here. So 10 minus 2 minus 3 minus 2 is 3. B minus 1 minus 1 is 3, right? 7 minus 2 minus 1 minus 2 is 2, right, over here, right? So take note of that, right? Now as we continue, we can actually calculate the content of the matrix need, right? Which is defined to be the maximum minus the allocation. So let's look at the need here. Need is basically maximum minus allocation for each process and resource, right? So the need basically here would be 743, right? So how do we find out what's needed, right? So if we look at this current snapshot at time t0, right? So we need maximum that the process requires is 753, right? And currently allocated is 010. So how much more does it need? It needs 7 of A, right? It needs 4 of B, and it needs 3 of C, right? So 5 minus 7 minus 0, 5 minus 1, and 3 minus 0, right? So you can see P0 has 743. What about P1, right? P1 here is the same thing. It needs a maximum of this one, right? It already have it needs 3 of A, right? You already have 2, so it needs 1, right? And 2 minus 0 and 2 minus 0, so it will be 1 2 2. And if we look at the slides, it's 1 2 2, right? So similar for P2, right? So P2 requires 902, right? So 9 of A, it already have 3, so that's 7. 0 minus 0 is 0, 2 minus 2 is 0, so it's 700, right? Oh, sorry, let me do that calculation. 9 minus 3 is 6, sorry. 9 minus 3 is 6, so it's 600, right? Same thing here. This would be 2 minus 2 equals to 0, 2 minus 1 equals to 1, 2 minus 1 is equals to 1. So what P3 needs is 0 1 1, right? So you can see that's 0 1 1. Now for P4, we can see 4 minus 0, 3 minus 0, and 3 minus 2. So that makes it 4 3 1, right? So you can see that it's 4 3 1, right? So the system is a safe state since the sequence, there is certain types of sequence that would result in a safe state, right? So consider this, right? So right now we have 332 that is required, right? That's still available, right? With what is currently allocated, right? And what is currently needed, right? So if we look at 0332, we can allow who to run basically, uh, P1 to run, right? Because 332 is still lesser than 122, right? And so on. So if P1 gets to run, basically P1 finishes and it will release all the resource that it will be allocated, right? All right. Let's go through this algorithm later, right? In a bit in the next session, and we'll go through step by step how this criteria is classified as safe or unsafe, right? So I'll see you in a bit.